that's not what I'm going to talk about. I'm going to talk about how we use it internally. So who am I? This is me in my natural state scheme. I'm a software engineer at DigitalOcean. I'm on the Platform 4 team. Our sort of mission is to develop and build runtime platforms and tools for all the other teams inside DigitalOcean. So we're focused on sort of making it really easy for other people to write business stuff. We don't develop business stuff, we run Kubernetes clusters. My background is working in a bunch of different startups. First, I had sort of a DevOps role with a bunch of microservices. And I thought, like, there's got to be a better way to do this. And about that time, I figured out, or found out about Kubernetes, and sort of started playing around with it. The next job I took was doing basically on-prem installations with Kubernetes. It's really powerful for both sort of small installations and huge installations. I've also worked remotely for 6 years at this point. As I wrote this, I thought maybe I should have given a talk about that instead. So yeah, I will briefly cover what Kubernetes is. I'll probably speed through this so we have time to talk about more interesting stuff. So Kubernetes is a container orchestrator. It gives you a way to run containers across sort of a wide variety of compute resources that you pull together. It does things like automated deployment, scaling, and connecting your applications. So the general concept is it aggregates your compute resources. So that means you can bring all your servers into Kubernetes and sort of treat them as a pool of resources to schedule your work across. Kubernetes gives you ways to schedule work and then reschedule work if like you lose a node or something like that. There's also a large variety of primitives that are sort of useful for building distributed systems. So there's things like a deployment or, well, I'll talk about it next slide. So the sort of lowest level primitive is just a single container, which is like a Docker or other container. And then a pod is what you sort of deal with the most. That's usually one container, but it could be more. Containers in a pod share resources like they're sort of on a local machine together, so they can read and write the same file system, things like that. A deployment is sort of how you define your services. That's sort of the top level object of a service. It's a group of pods. You can make them scale up and down. You can have just one pod in a deployment, or you can ask for 10 pods, 100 or 1,000 or whatever. There's also services in Kubernetes, which are virtual IPs that point at the deployment. So it gives you sort of like load balancing out of the box. Here's a diagram I found that sort of somewhat sums up how Kubernetes works. So you've got this sort of master control plane, and then you have kubelets, or the nodes in your cluster. And on them are pods running inside Docker. And they can be, like I said, one or more containers sort of sharing resources.
Are nodes like servers or VMs?
Yeah, so they can be servers or VMs. I'll talk about both, actually. There's a bunch of other primitives. There's like jobs. If you want to create a batch task of some sort, or even a scheduled task, you can use jobs that are like run once to completion, things like that. There's namespaces, which just give you the ability to sort of segregate and isolate your resources. This is really useful. You can have a single set of computers that you turn into a Kubernetes cluster, and you can have a dev, staging, and production environment in the same place with the same identical things, just sort of isolated from each other. That's maybe not really the best practice, but it gives you a lot of flexibility, especially when you're dealing with a lot of people, a lot of applications on a single cluster. There's also custom resources, which are really powerful, and I'll talk a bit more about later. But you can create basically just arbitrary API objects in Kubernetes and sort of read and write them, watch them, and react to their creation or deletion. So I'll talk a bit about the background of how Kubernetes sort of got going at DigitalOcean. I'm also going to talk about DOCC briefly, which is an internal sort of tool we've built to make it easier for developers to use our Kubernetes clusters. So at DigitalOcean, about 2015, companies growing really fast. There's a ton of applications, there's a ton of teams, there's a ton of ways to do things. If you want to start your own service, you just like pick whatever you're familiar with and put it together, and this is kind of a nightmare. At the same time, containerization was getting really popular. gaining a lot of like momentum. And then there was also sort of more mature tooling evolving around scheduling and running containers in production. Specifically Kubernetes, Mesos. We had teams using Kubernetes and Mesos internally just as like one-offs, like they decided that that was a good idea for their thing. And so our team was chartered to provide this sort of standard runtime, provide a bunch of building blocks for people to get going if you want to, write a billing service or write an email reporter. We want to give you the things that make it easy for you to do that so you can focus just on your code and we'll worry about like making it work and making it run. So DOCC is I think it stands for DigitalOcean Control Center. Sometimes I call it Docc, so if I say Docc or DOCC, same thing. This was sort of our internal interface to Kubernetes. So at the time, we weren't really sure that Kubernetes was what we wanted to end up with. Mesos, like I said, had users in our company. There were some strong proponents of it. So we wanted to also make sure that we could sort of like change out the back end of whatever we decided. The big wins are that it's multi-tenant. Instead of having teams spin up virtual machines for, if they want to create a service, they spin up a set of virtual machines, have to manage them. Instead, we can create the infrastructure and just let them run their stuff on it. It's somewhat stateless in that the only state we have is inside Kubernetes. So DOCC really just translates into Kubernetes resources and then out of it and allows people to deal with just sort of this higher level abstraction. It also does things like it handles off, so we can determine what team you're on and if you're allowed to deploy an application. DOCC is also really simple. Instead of exposing like all the knobs in Kubernetes, we decided to sort of like focus it on the ones that were most likely to sort of be important to you. It also promotes and enforces best practices. So we can, ensure that you can't use a Docker container with a tag at latest. I kind of personally think that's okay, but some people don't, and so like DOCC restricts you from doing that. Mostly it was built to sort of solve this happy path for a stateless service. So if you have complex storage needs, you want to run a database, that's cool, you're on your own. We want to make it easy for you to run sort of like the really sort of simple stuff that makes up the meat of all the applications we have. So why did we build this platform instead of just exposing people to Kubernetes? I covered a bunch of the reasons already, but here's sort of like the specifics of it. You can write a 90-line JSON manifest that looks really sort of friendly and human readable, instead of writing 300 lines of different YAML resources for a service, an ingress, a deployment, and all the things that sort of stitch it together. Plus, it gives you all these features out of the box. We will go ahead and implement monitoring for you. We will add logging and forward your logs to a remote log storage system. We'll give you a TLS certificate. We'll even rotate your TLS certificates for you. You can just get all this out of the box. So here's what a really simple DOCC manifest looks like. This is just sort of the important bits, give it a name, give it a namespace, say how many instances you want, say just give me a TLS certificate, and define how to ingress into the service. So our first Kubernetes cluster we're set up and running in January 2016, and DOCC has been a huge internal success since then. We run 1,200 applications on it across 20 plus clusters. We have a cluster or 3 or 4 in every single one of our data centers sort of across the world. At this point, we have even more memory sort of under management, probably 20 terabytes. And yeah, there's 75 different service owners sort of constantly deploying all their services all the time. If you want to find out more specifically about DOCC, there's these 2 great talks that were given at KubeCon. The first one by my manager, Mac. That's a great talk specifically about DOCC. And then the other one by Eunice is also a pretty good talk. So as we've seen this huge adoption inside DigitalOcean, we've had to sort of grow our clusters. Original clusters were all built out of droplets, so the same droplets that you could go rent by the hour. We use them. So they're virtualized nodes, which have huge pros and huge cons. Mostly we get to use Terraform, which is great. You can sort of dynamically spin up a droplet, add it to your cluster, get a little more capacity. The downside is that the networking model is much more restrictive. So specifically, services are only directly routable from inside the cluster. This is because Kubernetes, in this sort of original setup, uses an overlay network, which is basically a virtual network that's internal to the cluster. So things outside of it don't really know about it, and you can't reach those things. So here's an example. If I look up a service running in our cluster Jinx, I get this IP, and I try and connect to it just from my machine. It doesn't work. That IP is not routable. It's only routable from other pods running inside that cluster. To get around that, we use ingresses, which are basically a load balancer into the cluster. They work really well, but they're sort of restrictive. All your traffic has to go through your set of load balancers, so it's not necessarily ideal. On top of that, the overlay network adds just layers of encapsulation to packets, so it adds a bit of overhead. You lose the source IP when traffic is leaving the cluster. So if you have some database and you see that you're getting inundated with connections from this IP and you look it up, you could find out that it's one of our clusters. And that's it. You can't find out what it is inside there unless you do some digging and look through the machines. So we started looking at building bare metal clusters. These are the Ferraris of compute nodes. So we get huge machines that have up to 48 cores or 128 gigs of memory. We can pack way more services on there than we can on a 16 gigabyte or 32 gigabyte virtual machine. Also, the services are resolvable and routable from anywhere because we've sort of connected the networking inside Kubernetes to the outside world. Here's the same example. I can look up the same service, but running in a different cluster, one that has this networking setup, and I get a 404, which in this case is good, because I can actually route to it from my machine. So the way that we do the networking is we use this project called KubeRouter. You can run it in your cluster, and if you have sort of the right network topology set up above it, you can do BGP advertisement of all your pods and all your services. This means that any pod or service is basically like a first-class citizen on your network. It's the same as if it were running on a virtual machine on the network. It just has an IP. It looks like any other sort of addressable computer. This also makes the DNS resolvable externally. So we can configure our DNS servers to point at the inside Kubernetes named servers. So you can look up a service by name, not just by IP. Just recently at the last KubeCon, I think last month, my teammate Andrew gave an awesome talk that's just a deep dive on how we did all this networking. He sort of run that from the beginning, so it's definitely worth checking out. I think these slides will be posted later if you want to watch any of these talks. So I did promise I was going to talk about Kubernetes and not just DOCC, so let's move on a bit. So I was looking for a good picture of choke point, and I turned around, and my dog Bubba was right there. And I was baking bread at the time, so I kept going in and out of the room, and he wouldn't move. So I snapped a picture because it was perfect. So what's wrong with DOCC? It's an on-ramp. It makes it really easy to get up and running. It makes it easy to take your service with minimal exposure to all the gory details of how it's running on Kubernetes. But it's kind of a choke point still. You're restricted to, if you want to use a feature that we haven't implemented in DOCC, you can't. You have to file a bug report or a feature request and wait for us to add it. Even if it's really simple, it's still just sort of a blocker. It's also opinionated. We think our opinions are pretty good, so hopefully that's fine. But there's valid reasons to do things different ways, and so DOCC sort of gets in the way of that. There's also restricted access just to the underlying Kubernetes stuff, we have to go look up and do the sort of advanced debugging if you can't immediately determine what's wrong from the logs that we show you, and there's something more complex with your service. It sort of requires our involvement. And also, like, bugs are a blocker. If we make a tiny bug in our sort of DOCC software, that could end up blocking your access and deployment, which is not great. At the same time, Kubernetes has gained huge industry adoption. This is a picture from the last KubeCon. In fairness, that is the meal line, so maybe everybody's there for food. But we have definitely decided that we're sticking with Kubernetes. Like, it works super well for us, and we don't think that there's any realistic chance that we would switch out that platform underneath. So at the same time that we're really confident in what we're doing, we also have engineers that want to learn how to use Kubernetes, especially as DigitalOcean has a public Kubernetes offering coming out. So their company is building something and they want to be able to use that thing. We also hire people that already have experience with Kubernetes at this point. And at this point, it's a super stable underlying platform. Like I said, there's no way we're going to change it out. Additionally, this sort of falls under the opinionated thing, but there are more advanced services that have more specific needs, and we want to support those without necessarily spending all our time developing this DOCC platform. We really intend it to make things easy for people, not to stop people from doing other stuff. So if you have some sort of complex networking requirement, like if you want to do, I don't know, netboot into your service, or use your service to serve droplet images, that sort of falls outside of something that we could support out of the box. If you want persistent storage, if you want to run a database or a set of databases, a database cluster, that's something we sort of support, but we'd really recommend you do it a different way. Namely, using something like a stateful set, which is sort of a newer Kubernetes resource that allows you to have a persistent identity with a pod. So you can sort of always be guaranteed a name and an IP address that are the same. Also, disk that's the same, and you can associate with that. Also, if you want to build complicated things that use these custom resources that are available, there's no real way to do that with DOCC. And so we decided that, about 6 months ago, maybe a little longer, we really wanted to make a push to open up Kubernetes to the rest of the company. We still want to give you this Onramp, but we want to get out of your way. So the original access for people using the cluster, early on we agreed that some people should have access to the clusters, to the direct primitives in Kubernetes. So we would manually create a namespace, manually create permissions, give someone a certificate, encrypt it and send it to them. It was kind of a pain. Paperwork. In Kubernetes 1.8, they introduced RBAC, or role-based access control. So this is a great building block for us being able to give permissions out. We can define, some role is allowed to read, write, delete, these kind of things. And so this gives us a lot of flexibility to be able to sort of give out these permissions, something short of you have no access or you're an admin. And using the Docc project, which CoreOS put together, we can connect our LDAP server straight into Kubernetes auth. And so this enables people to just run a Docker image, type kubectl auth. I think I even show this. No, I don't. Type kubectl auth or plug in auth. They get redirected. They log in with their LDAP credentials, and then they're given a token. And all of a sudden, they can read anything in all the clusters. Here's an example of an RBAC policy. It's not very interesting. Yeah, so there have been a bunch of challenges that have come with having this many different or this sort of breadth of clusters. It was really nice when we had just droplet clusters and we could use Terraform. We could just manage all the state files in a shared place. And it was really sort of straightforward to expand, add capacity. These new hardware clusters are a little bit more complicated. They involve things like budget. You have to go talk to somebody to buy a bunch of servers. You have to put in an order. It takes time. So they're a bit less flexible. And we have to get a little bit better at managing our resources and sort of doing capacity planning. We use Chef for everything at this point. I think we'd like to sort of move away from that, just because nobody really likes Chef that much. But honestly, it's a pretty decent fit for setting up Kubernetes nodes. Kubernetes has this reputation that it's like horrifically complex to set up, and like there's all these tools, like kubeadmin, and there's some other one I forget, that like sort of make it easy to provision a cluster because it's just so impossible you never want to do it yourself. But really it's like you have to run etcd, and you have to run like 5 processes on 1 or more nodes. You have to do a little bit of like dancing around associating the right certificates, but it's pretty straightforward. Like it is 5 to 6 services that you have to run, but it's not rocket science. So our Chef cookbooks just do that. You assign a role to a node and it puts the services there and sets them up. So our configuration at this point is automated with a lot of shell scripts and like a CI system. Basically just, we manage our resources in Git, and then we can sort of apply them when we deem fit via some CI runner to all of our clusters. We try to keep the clusters mostly identical to make this easier. So there's really only a small set of things that vary for each cluster. For the most part, they all run the same things in the same way, in the same places. But there's, even then there's a large set of applications. Like as we develop a new application or a new thing that we want to add to our clusters, we sort of have to figure out like, so this sort of works. We want to run it in our dev cluster, but now it's different from our production cluster, and then we have to worry about things like that. So to that end, we've started building this software called Rackham. By the way, if you haven't watched Black Sails, it's a really awesome show. If you like pirates. Rackham is sort of analogous to like Chef or Puppet or Salt for our cluster resources, like the actual YAML files that we use to set things up. It provides consistency of state so that we can specify, apply this git ref everywhere. We can also make sure that things don't drift, like regardless of what someone has gone and done by hand to some cluster, just always apply this state. We can also use this to sort of like deploy things. If the git resources change, trigger, running this update. So Rackham is a controller. That's sort of like a loosely defined term. Basically what it means is it watches these custom resources. We develop a custom resource called a waybill, and then this process watches for new ones. And once it gets one, it sort of reads its specification of like, here's what I do. And then when it runs or when it's triggered, it goes and does that thing. We'd really like to open source this because there's sort of this big chasm between things like Helm, which are sort of like overwrought deployment configuration tools, and then like running kubectl by hand or with a shell script. So I feel like there's sort of this missing tool in between, and that's what we've sort of tried to develop Rackham to be. Here's just a brief example of like this custom waybill resource. So like I said, you can make these custom resources. They're totally arbitrary stuff. We have just made up everything inside this, but it lives inside Kubernetes, and you can interact with it using kubectl. You can interact with it using the Kubernetes API. It's really handy to just have to be able to use this as a data store. So it's a custom resource, type waybill. It's a simple resource. We have a couple types of resources at this point. Simplest one just literally runs kubectl apply of whatever you give it. So in this case, we specify some paths in a Git repository. So it will check that out, check out that ref, and just apply it. And then it will, update the status. It'll say, here's the ref that I know about, here's what I've applied, and here's sort of the output of when I ran that. The really important, to me, thing about Rackham is it does templating, that's the piece specifically that's missing the most out of all the sort of existing Kubernetes tooling. There's no really easy way to say, hey, when I apply this resource, instead of hard coding, I want 3 DNS servers to run. Just say like, I want however many are specified in that config map to run. So you can sort of isolate your differences to a single place, like a single config map. Specifically, we built this mostly to solve Prometheus problems. We have dev clusters that are 3 nodes, and then we have some production clusters that are 100 nodes. So the amount of applications that runs in each is vastly different. And so we have a Prometheus sitting there scraping metrics. In large clusters, it takes like 50 gigs of memory. So we want to make sure that we request the right amount of memory so we can place it in the right place. But in a dev cluster, we don't have any nodes that even have 50 gigs available. So we want to request 1 gigabyte. I'll talk a little bit about future improvements. Looking forward, there is federation sort of in the planning stages upstream in Kubernetes. This would enable us to connect our clusters and sort of administer them as more of like a sort of single unified unit. I don't know exactly what that looks like in practice, but having one thing that we manage that has like sort of a variety of differences inside of it certainly seems a lot simpler than having 20 completely separate, discrete clusters. One thing that we could do right now, but we haven't done, is if a team has really specific needs, like if somebody wants, let's say we get like our data and analytics team, they want to spin up a huge analytics stack, they're going to need 500 terabytes of disk or something. We can enable them to just sort of bring their servers into our clusters. We can sort of segregate those resources out and say, here, they're part of Kubernetes, you can use DOCC to talk to them, you can use kubectl to talk to them, but nobody else will use them. They're your servers, they just run in our cluster. That is my rapid fire overview of Kubernetes. I would love to talk more about it and answer any questions you have.